Well, good evening and welcome to UW Space Place. This is one of our guest speaker nights, and I would like to introduce Professor Ed Churchwell of the UW-Madison Astronomy Department. Recently retired from that department, but he came to Madison from Germany, from the Max Planck Institute, and in 1977, and has been here ever since, during which time he's done a lot of really important research here. Primarily as well, I shouldn't say primarily, as a radio astronomer, certainly, but here at Space Place you can see a lot of exhibits with Ed's fingerprints on them because he was very involved with the Spitzer Space Telescope and a project called GLIMPSE, mapping the Milky Way, the plane of the Milky Way galaxy. So I'm really pleased to introduce Ed tonight. He's going to give us a talk on basically cosmology and how astronomers can figure out how the universe has evolved since its origin. So let's welcome Ed. Thank you.
Okay. Thanks, Steve. Well, thank you very much for coming out, particularly on a rainy night like tonight. This is a topic that I could spend a whole semester on, okay? So I'm going to try to distill some of the main components of what we've have at our disposal to understand how the entire universe, in fact, has changed from an instant after it was born until to the present time and on into and project the future. So hang on to your hats because you're going to go through a fantastic journey here, and please, if you have questions, interrupt, and I'll be glad to try to answer them if I can as we go along. Okay, Mark Twain once made this famous statement: "There's something fascinating about science. One gets such wholesale returns of conjecture out of such trifling investment of fact," and that was certainly an apt description of cosmology in the first half of the 20th century. The idea that we can determine the properties of the universe as a whole, a tiny fraction after its birth, is presumptuous to say the least. But in fact, that's precisely what cosmology tries to do. So, surprisingly, the history of the universe can be described based on 6 quantities that can actually be determined from observations, luckily. And I'm just going to kind of point out quickly what these are. H0 is what's called Hubble's constant. It basically is a measure of how fast galaxies or clusters of galaxies are receding away from us as a function of their distance from us. Okay, and that's a fundamental quantity, and it's one that's easily observed. In fact, was first observed in 1929. The omegas here, one is omega sub r, means for radiation. It's the fraction of energy density in the universe in the form of radiation or photons. And the naught here means that these are quantities that we measure at the present time, okay? So the naught means they're the quantities we measure today, but if we can measure them today, we can project them back at any other time. And that's a key issue, mainly because if we can establish that the universe was in thermal equilibrium, then we can determine all these parameters at any given time. The omega m here is the fraction of energy density in the universe in the form of matter. Okay, the omega sub lambda is the fraction of energy density in what we call dark energy. And I'll come back to all of these in a moment. Q naught it's called the deceleration parameter. So it's a parameter that determines what the rate of slowing down of the expansion of the universe is. And basically, it's not an independent parameter. It really depends on omega naught. So if we could determine omega naught, which is the sum of all of these 3 omegas I'm talking about here, then we also know Q naught. And T naught is the temperature of the universe as measured today. So let me move on now. So The observational underpinnings, there are about 6 kinds of observations that have been made that actually determines these properties and tells us how to go about using those properties to say what the universe was like at any given time. One is what's called the universal expansion, or Hubble's law, which was first published in 1929. And he got H naught a little wrong, but he certainly understood the principle. The other is the abundance of the light elements of primarily deuterium and helium. And that was something that first kind of came to light in the 1950s. And the other is dark matter, the detection of dark matter. Is that me? No, oh, sorry. Okay, this light's in my eyes. I'm trying to move out of the light. So dark matter was first actually detected in 1933 by a Swiss astronomer who was working at Caltech at the time, and was looking at the motions of galaxy in a cluster of galaxies, and realized that they were moving a lot faster than they should be moving based on the amount of light that they were producing. In 1939, another astronomer I'll get to in a moment also found roughly a similar sort of thing, but basically by measuring the rotation rates of spiral galaxies, and he found that they were rotating much faster than they should. And in the 1970s, Vera Rubin did a very detailed study of the rotation of galaxies, and basically found that the only way you could understand the rotation rates is if there was more matter there than you could actually see from the light that's produced by stars. And I'm going to kind of go through these a little bit more in a moment. So the large-scale distribution of matter, the cosmic microwave background, let's come back to that, that's an important one, was first detected almost by accident in 1965 by 2 radio engineers, actually, at Bell Labs. And basically what they measured was the temperature of the universe at present time. Then the large-scale distribution of matter, that is, how clumpy is the matter distribution in the universe, and it turns out that it's not smooth, at least on a what we call it from an astronomical point of view, on a small scale. Large enough scale and it looks pretty smooth, but it ain't necessarily so. The recession velocities of type 1a supernova is used. Those are standard candles. There's objects that have well-determined intrinsic brightness, and so if you have that, you have a standard candle so that you can turn from the apparent brightness, you can determine what the distance is. Okay, so those are the 6 kind of main observational underpinnings. And I'm just going to quickly run through this. Universal expansion basically was done by Hubble and Hummus in 1929. And they found that the velocity, the recession velocity that you can measure through spectroscopy, is basically disproportional to the distance of the galaxies. And so this H naught is the key parameter here. So if you just take the velocity which you can measure, and you have to be able to measure the distance independently in some way, but there are ways to do that. And so H naught is just V over D. And so that's what was used to determine this. This result, however, implies that the universe is much, much smaller in the past, i.e. The mass densities were much greater than they are today. Now also, if the universe is expanding, and you're not changing the total energy in the galaxy, what happens when you take a gas under pressure and you let the pressure off? What happens to the temperature of the gas? Goes down, right? And that's exactly the same thing that happens in the universe. The universe started out as something incredibly dense and hot and massive, and then has been expanding ever since. At one point, it was explosively expanding. And so as it expands, it also is cooling down. And so that's the key component of our understanding of the evolution of the universe. Expansion here, you got to be careful. It doesn't mean, it's not like the motion of galaxies through space. It's space itself that's expanding, okay? So it's like the There are several examples that are given, but that people use. But one is if you have a loaf of bread with raisins in it, you start to cook the bread, and the bread rises. The relative positions of the raisins don't change. They only change in their separation, right? But the pattern doesn't change. And this is the same sense we're talking about for the universe, that it's space-time that is expanding, not the motion of galaxies through space. Think about that. Okay, abundances of the light elements. Those elements, deuterium and helium, can only be understood if the early universe was hot and dense enough to have been a thermonuclear furnace, and therefore has cooked the hydrogen atoms and produced helium and deuterium. The stars can't produce enough of this of the amount that we actually see. Okay. So, and this is consistent with the idea of the expansion of the universe. If you go back in time, the universe had to be hot and dense. And at some point, it had to go through a period where it was dense enough and hot enough to actually behave like a thermonuclear furnace. Okay. Alpha, Hermann, and Gamow, based on the realization that the early universe was hot and dense enough to sustain nuclear reactions, to convert hydrogen to helium and possibly heavier elements in the 1950s. And they actually even predicted roughly what the temperature of the universe should be today. And they estimated somewhere at 5 to 7 degrees Kelvin. And you'll see in a moment that we have a very precise number for that now, and it's about 3 degrees. Dark matter. Fritz Zwicky in 1933 found that the velocities of galaxies, I've already gone through this, so I'm going to zip through it fairly quickly, but so that you see, though, there are several players in this area. Vera Rubin in the 60s and 70s basically did this systematic study of the rotation of spiral galaxies, and concluded that there's a lot of unseen matter in the universe that we don't see, with our telescopes. This is the idea, however, right here, that if you look at the rotation rate of spiral galaxies from the center of the galaxy outward in radius, what you would expect if all the matter was confined to the nucleus of the galaxy, it should go like the curve A that I show here. This is how the planets move around the sun. They go as 1 over r to the 1/2 power. But that's not what happens. The rotation rate stays up here flat, much higher rates of rotation as you go outward than you would expect. And the only way that can happen is if you're enclosing more and more matter as you go further out in radius on these spiral galaxies. Okay, cosmic microwave background. The radiation temperature of the universe today is about 2.735 plus or minus 0.005 Kelvin. We know that very precisely now because of basically the Planck the COBE satellite in 1990s. But anyway, the fact is that you can look in this direction, any direction in the sky, and you get exactly the same temperature, or you get exactly what's called the Planck function. It's a function that tells you the brightness is a function of wavelength. And we know that very precisely, and I'm going to show you here. So the cosmic microwave background is really a picture of the universe when it was about 280,000 years old. Okay, you can look back into space, and at some point you run into a wall where the universe becomes opaque. You can't see any deeper because it becomes opaque. And at that point, if you take a map of the sky, what you see is this microwave background that's only about 2.73 degrees, but when it was 280,000 years old, it was very, very hot. But today we see it for only 3 degrees because the stretching of space-time has stretched out the wavelength now to where it's equivalent to about 3 degrees. Okay, so, and it also, important thing, that tells us, however, that the universe was in complete thermal equilibrium at that time. So we can use this idea, using basic physics to trace back in time or go forward if we wish. Here, just to let you get an idea, though, of how precise a measurement this is. This is one of the most precise measurements you're going to see in the natural world. The dots that you see in that curve are measurements from the COBE satellite. The curve is a Planck function. That's the theoretical function for the brightness of an object at a given temperature. Take a bar of iron and heat it up, and it goes from very dull red to a bright red to a yellow to white. And that's a Planck function, okay? It's determined entirely by one quantity, the temperature. It doesn't matter what it's made out of, anything else, except the temperature. So that's the curve of the brightness of the universe as seen today. And it peaks at about 2 microns, or 2 millimeters, I'm sorry. Okay, so here's a picture of the universe, or of the cosmic microwave background when it was about 380,000 years old. And you see all the orange or reddish dots are a little bit warmer. The green's intermediate and blue is a little cooler. But the amount of deviation from a single temperature is tiny. It's in the 10 to the minus 4, 1/10,000th from top to bottom here. So these are little ruffles, which ultimately later on are going to become galaxies and things like that. So view of the universe, I've just shown you one at about 380,000 years. Going back and even further in the past, the universe is basically just a hot thermal cauldron of subnuclear particles. And then if we go to present day, the universe looks like the bottom picture there. So this is a kind of a very quick thumbnail picture of the change in the universe. But a lot of changes have occurred, and I want to go through a few of those. As I said, one of the other things that we want to know is the distribution of matter. How clumpy is the matter that's distributed in the universe, and on what scale? And basically, ultimately, what happens here, as we'll see, is if you're thinking about the universe as space-time expanding with time, and gravity operating with this expansion, what happens? Well, a lot of simulations have been done, and basically what should happen is that matter starts to form into filamentary structures and things like that. And so it will not be smooth. Matter tends to want to gather together with gravity. And so we want to know if that in fact is what happens. And these are observations now of galaxies. And there were 3 surveys here. This inner one had a fairly wide angle. And all of these little yellow dots here are galaxies. And you see that they're not smoothly distributed. They are kind of filamentary. And there's a second survey that was a little bit narrower piece of sky, but going deeper. And you see that, again, matter is not uniformly distributed. Galaxies are not uniformly distributed. They're in kind of filamentary structures. And then an even deeper survey where you start to run out of galaxies out there, not because there aren't any there, but because it's a sensitivity issue that you can't detect these very distant galaxies so easily. But you see, again, even no matter where you look, the distribution of galaxies is not smooth. It's filamentary. But of course, if you add this up over a long distance, a large enough volume, the universe does look kind of uniform. And that's important because all the relationships that we use make 2 assumptions. One, that The universe is isotropic. That means it doesn't matter which direction you look, it looks the same. And it's uniform. It is uniform density. And as I say, you've got to now think, however, cosmically in order for that to be true. This is a simulation using basically just the idea of expansion of the universe and cooling and gravity. And this is what simulations tell you should see. Okay, what are the tools needed to understand the evolution of the universe? Well, application of well-established physics, okay? Nuclear physics, high energy physics, relativity, thermodynamics, and so forth. But none of these are things that are mysterious or are not understood, okay? So we can understand the universe using pretty straightforward physics. One of the key ones here is this physics, what's called the physics of annihilation and pair production. An annihilation, it turns out, is independent of temperature. It doesn't matter. Once the temperature becomes low enough, some particles will annihilate with their antimatter particles. Matter and antimatter particles will annihilate each other. And if there were equal numbers, we would not have anything left in the universe. It would all be in the form of photons. Pair production is strongly dependent on temperature. Pair production is when you have two photons that collide with each other, and if they're energetic enough, they will produce a matter and an antimatter particle, okay? But they've got to be hot enough. The particles have to be moving fast enough or have to be hot enough to be able to have the equivalent energy of the mass particles that's produced. And so basically the temperature has to be greater than, it's proportional, greater than the some factor times the mass of the particle that's actually produced. That's the key. So one of these is incredibly dependent on temperature. The other is independent of temperature, and so this makes for an interesting evolution of the universe. So these threshold temperatures, the neutrons can be produced by colliding two photons together, that as long as the temperature is greater than about 10 to the 13th Kelvin. Protons are a little less massive, and so they have to be hotter than about 1.088 times 10 to the 13. So there's not much difference, but there is difference in mass, and therefore the difference in the threshold temperatures. Electrons, of course, are much less massive, and of course their threshold temperature is substantially lower. It's about 6 times 10 to the 9th, or 6 billion Kelvin. Okay. So the cosmic temperature today implies the temperature in the past when the universe was much smaller and denser much hotter and much denser than today, of course. And you can infer the temperature back to very, very small fraction of a second. So temperature is basically disproportional to, it should be 1 over the square root of the temperature here, of time, of age of the universe. So it should be a square root over the t, the little t. Okay, so the equation of motion that includes all of the constituents of the universe, that means baryons and dark matter, radiation, neutrinos, dark energy, and so forth, can be solved, and we'll come to that in a minute. So let's talk about the evolution of the universe. And the earliest point at which we can say anything at all about the universe is about 10 to the minus 43rd of a second, okay? So that's like dot with 43 zeros after it and 1, okay? So it's a tiny, tiny fraction of the universe. But believe it or not, we think we know roughly what the universe was like at that point. We can't say much beyond that. The reason is because we're not sure how the forces of nature, for example, were. I mean, the presumption is that the four forces of nature were basically just a single force at this time. We don't know how those subnuclear particles would react with each other under these temperature and density, and with the knowledge of, for example, we don't know enough about gravity at that stage. So that's the earliest moment we can determine the properties, and we're not sure how particles interact with each other. Okay, but we can say one thing, that the universe at this instant had to be made entirely of fundamental particles. That is, the particles that can't be reduced anymore. And what are those? Well, they're electrons, neutrinos, quarks, and they're antiparticles, and photons, and possibly gluons. Okay, we're going to now go to a time of about 10 to the minus 32 seconds. This is what's called a period of inflation. Temperature is about 10 to the 21 Kelvin. The temperature here is too high for protons and neutrons to be stable. So what you have are these free quarks that are moving around in space at very high velocities and very high densities. And if you form a neutron or a proton, they would be broken down immediately because they're being banged into each other at such high energies. The universe has cooled from the time that I told you, 10 to the minus 43 seconds, by about a factor of 1,000,000 or so, and increased by size by tens of orders of magnitude. Now, the universe at this time is basically explosively, it's starting to explosively expand. Nobody understands exactly why this is true, but it's called the period of inflation. And the universe expands at a rate that's faster than the speed of light. Now you may ask, how can that be? Well, remember, we're not talking about motion of particles through space. We're talking about space itself. The rate at which space can expand or contract is not controlled by the speed of light, okay, or by the theory of relativity. And so the universe must have gone through this period of what's called inflation, where it may have expanded by, like 25 orders of magnitude in, tiny, tiny fraction of a second. So quarks and antiquarks are beginning, by the way, quarks are these particles. They're very strange particles, but they are fundamental particles as far as we can determine. And protons and neutrons are made of combinations of 3 different quarks. There's another set of particles called mesons that can be formed out of combinations of 2 quarks. And but at this point, they're free particles, and that's something that we'll probably never see again in nature. Okay, so they're beginning to be bound into protons and neutrons, and they're antiparticles. As a consequence, do not undergo what's called freeze out. That is, they no longer are going through they don't go through a period of annihilation and pair production. Precise time when this occurs is not all that well established yet, and I'm not going to say anything more about quarks. Now we're going to jump down to 10 to the minus 12 of a second. Temperature now is about 10 to the 15th Kelvin. It's a factor of about 1,000,000 cooler than that other time point. Quarks have combined to form protons and neutrons and mesons, and they're antiparticles, leaving no free quarks. Electrons, neutrons, protons, neutrinos, and their antiparticles are stable and freely interact with radiation, and so you have pair production and annihilation that's going on at exactly the same rates. So they're annihilating each other and being formed through pair production at equal rates. And so it's a stable, completely, what's the word I want to use here?
Zero sum?
Well, zero sum would be a good term. They were in equilibrium. That's what I really want to say. Okay, so now we're going to jump down to 100th of a second. Temperature now is down to about 10 to the 11th Kelvin. And this is below the threshold temperatures of neutron and proton pair production. And so they're rapidly disappearing from the universe, okay? because they no longer can be formed by pair production because the temperature is getting too low, but they can annihilate each other, and they keep right on annihilating until there aren't any more. And so protons and neutrons are disappearing. And the only thing that saves them is the fact that for some reason that we still don't understand, there was just a tiny little bit more matter particles than antimatter particles. And so all the antimatter particles disappear, and you get a tiny residual of matter neutrons and protons. It's about 1 out of every billion particles. Okay, so this is a key issue. Now, so these what we call when this happens is what we call freeze out. The university's gotten too cold to make more of these particles out of photons, and so they freeze out from the universe. And to begin with, the number of neutrons is about equal to the number of protons. But neutrons, when they're not in an atomic nucleus, are unstable and will decay at something like 11.7 minutes or something like that. And so it produces a proton and an electron when it decays. And so you start to see then a change in the neutron to proton ratio. And this is important because that will ultimately determine how much helium the universe will be able to make. Okay, so the density of the universe is about 3.8 times 10 to the 9th grams per cubic centimeter at this time. And if Mount Everest were made of matter this dense, it would actually just destroy the Earth. It would by tidal forces. Okay, the doubling time for the universe is about 2/100ths of a second. And at this time, there are about 1 billion photons, electrons, and neutrinos for every proton and every neutron. Okay. The size of the universe we don't really know, but we can say that the universe at this time was something like 300 billion times smaller at this time than it is today. Okay, go to 1/10 of a second. Temperature now is reduced to about 3 times 10 to the 10th Kelvin. Contents of the universe now is electrons, positrons, neutrinos, antineutrinos, and photons. Protons and neutrons and their antiparticles have essentially disappeared, leaving behind this tiny residual of about 1 billionth. So for, they're less than 1 billionth of their original number. Let me just move on. So all particles are still in thermal equilibrium. They have the same temperature as the above threshold temperature. I'm just going to go through this fairly quickly. The doubling time of the universe now is about 2/10 of a second. So you see that the universe is already slowing down in its doubling time, or its rate of expansion. And it continues to slow down because the universe is expanding against its own gravity. And the temperature and matter density continue to decrease as time goes along. And the neutrons are starting to get out of equilibrium, or they're getting fewer neutrons than protons with time. Now at about 10 to the 10th Kelvin, at about 1 second, the threshold temperature of electrons and positrons now are beginning to annihilate more rapidly than they can be formed through pair production. And so electrons are starting to disappear. It's still too hot for neutrons and protons to combine into atomic nuclei. So these are all just subnuclear particles. Nuclei can't hold together at these high temperatures and densities. Density is about 4 times 10 to the 5 grams per cubic centimeter. Water has a density of about 1 gram per cubic centimeter, right? So this is 3 times 10 to the 5 times more dense than water. Doubling time is about 2 seconds. A decrease in temperature has allowed the proton to neutron balance to become 24% neutrons and 76% photons, or protons, I mean. Now we go to about 13.8 seconds. Temperature is about 3 times 10 to the 9th K. Here we're below the threshold temperature for electron and positron production, and so they are rapidly freezing out as well. So now the electrons are disappearing as well. And this does add some energy. Each annihilation adds about a half of MeV of energy, which actually raises the temperature of the universe by a little bit. Okay. Neutrinos and antineutrinos at this time are more or less decoupled from the rest of the universe. They no longer interact with normal matter. You know, there's about 1 billion of these neutrinos that goes through my fingernail while I'm speaking. You know, at this instant almost. There's a lot of neutrinos, but they don't interact with us, and so we're completely, mostly unaware of it. Okay, so let's see. So from now on, when we talk about the temperature of the universe, we're going to be talking about the temperature of the gaseous components of the universe. And the temperature is still too high for atomic nuclei to be stable, and neutrons are still decreasing with time. So we go to 3 minutes and 45 seconds. Temperature is now about 9 times 10 to the 8th Kelvin. Still very hot. Deuterium can become stable, and so, but unfortunately its binding energy is not able to withstand the bombardment at these high temperatures, and so it doesn't actually form at this. It could, with as far as the temperature is concerned, but I'm sorry, it couldn't because the temperature is still too high. The bombardment energies are too high. Okay, if you can just plot as temperature versus mass, there's this short period where all these light elements can be formed, and this is kind of start out with protons and neutrons, and at this point in time of our temperature of about 10 to the 9th Kelvin, you know, all these things get to be made, and it's over a very short time. Okay, 34 minutes and 40 seconds. We have a proton-dominated universe. Temperature is about 3 times 10 to the 8th. Matter density is now too low to support nuclear processing, even though the temperature is high enough. All elements capable of being produced in the Big Bang have been made. The electrons and protons, electrons and positrons have been completely annihilated, leaving only a small residual of about 1 in a billion of the original number, the same as protons and neutrons. And that's this tiny residual is why we're here. It's because there was this imbalance. And as I say, we don't really quite understand why that imbalance was there. Okay. So the constituents of the universe now is photons, neutrinos, antineutrinos. Density is about 10 grams per cubic centimeter. Of this density, about 31% is in neutrinos and 69% is in photons. Okay. I'm going to kind of move on because I'm going to run out of time here. So the doubling times now of the universe is up to about 1.5 hours. Every 1.5 hours, the universe gets doubles in size. Okay, 7 times 10 to the 5 years. So we're jumping along. This is called the Dark Ages. Temperature now is reduced to about 3,000 Kelvin. At this temperature, the universe is cool enough for electrons to be bound to atomic nuclei, and so you have atoms formed. And once that's true, then suddenly the universe becomes pretty much transparent. Okay, and so this is a period when before star formation is really started, and there's gas that becomes atomic, and as a consequence, you have a dark universe. Okay, and so it's called the Dark Ages, and this is a change from a radiation to a matter-dominated universe. Okay, up until this time, the largest number of particles in the universe was photons and neutrinos. Since neutrinos don't interact, we're not going to say much more about them here. But at this point, when you start to form atoms, matter takes over as the dominant form of particles in the universe. Okay, now we go to about 1 billion years. This is a period of star and galaxy formation. Temperatures now drop to about 70 Kelvin, or about minus 200 degrees centigrade. Gravity has gathered matter into filaments and massive clouds that give rise to the formation of the first stars and galaxies. So that's at an age of about 1 billion years. At this time, it becomes possible for carbon-based life forms to appear in the universe for the first time. About 9 billion years ago, the solar system was formed in the Milky Way. And from about 1 to 9 billion years, it's possible that life could have emerged many places in the universe. Life on Earth arose at the age of about 10 billion years, about 500 million years after Earth's formation. But this would have undoubtedly been prokaryotic life forms, not the life forms like we're made out of, but more primitive life forms. The eukaryotic life forms didn't appear for another 2 billion years or so. Okay, current age of the universe is about 13.8 billion years, and the current temperature of the universe is 2.73 degrees. And I don't think I need to say any more about this. This is what I was trying to talk about a while ago, though. Time versus temperature. And the density of radiation is going down at a steeper rate than the density of matter. And you see there's a crossing point here. And that's when you convert from a radiation-dominated universe to a matter-dominated universe. The big T here is just the change in temperature with time. And that's determined entirely by the cooling due to expansion. Okay, now I'm going to do something that I should never do in a general audience. I'm going to write an equation down. It's a fairly complicated one, but I'm going to try to explain what's going on here. This is a relationship that was derived by Alexander Friedman, who was a Russian meteorologist who taught himself relativity theory and then started working on cosmology and wrote this very beautiful equation. It's called the Friedman equation. And basically what it is what's called the equation of motion of the universe. And so this h naught we've already talked about, and the h sub t squared is the Hubble constant at any other given time in any other time. Okay. Remember, it is a function of time. The universe is not expanding uniformly; it's slowing down. At least we thought this up to a few years ago. Okay, so that is determined by the sum of the omegas, omega r, radiation, omega mass, and the dark energy, omega lambda. But it has this dependence on this A factor. The A factor is what's called the scale factor of the universe. And it's basically all it is the average separation of, on a cosmic scale, of clusters of galaxies. Okay, so the average separation of clusters of galaxies, of course, is getting larger as time goes along. So that's a function of time. This is basically just determined by the expansion of the universe. And you can see that the radiation term here goes as this scale factor to the fourth power in the denominator. And so it decreases very fast in its importance in the motion of the universe. Similarly, for mass, omega m here is divided by a to the third power. And so it decreases very fast too, not as fast as radiation, but as we saw, the universe did convert from a matter-dominated to a radiation-dominated to a matter-dominated universe, and it's because of that dependence on A here. Omega lambda doesn't depend on A at all. And as a consequence, at some point, it becomes the dominant factor in the evolution of the universe. And this 1 minus omega naught is the sum of the other three here. So we're making the assumption that we know everything that's in the universe is either photons, matter, or dark energy. Well, we think we've determined what these three quantities here are, and so omega we believe is 1. And so that's the term that determines the geometry of the universe. And if omega is 1, that last term goes to 0, and that tells us that we live in a Euclidean universe. The universe is flat in that sense. Okay, well, I'm going to, this cosmic scale factor, I've already said what that is. You can convert this to a much simpler kind of expression, whereas this is the rate of increase of the scale factor. So it's just, it's a speed. And you can see it depends, when you write it this way, you still see the dependence on A, and when you write it this way, you see that omega lambda is multiplied by A squared. The others have A in the denominator, so they go down rather fast. Okay, well, anyway, that tells us, though, that omega lambda is going to become, and in fact is now, the dominant player in the evolution of the universe. Okay, I'm going to kind of skip some of this because I don't want to. I want to tell you what what's called the standard model of the universe is today, from all the measurements the best measurements we've been able to make. The current temperature of the universe is 2.725 plus or minus 0.001 Kelvin. H naught is 67.3 kilometers per second for every 3 million light years distance, increase in distance. And the age of the universe, as I say, is about 13.8 billion years. And Q naught is less than 0. And we're going to see that tells us that the universe is not slowing down. It's actually accelerating in its expansion. Because the omega lambda is the dominant term now. And it behaves, in a sense, like anti-gravity, if you wish. So the radiation term here, total, is only 8 times 10 to the minus 5. This is a ratio, remember. It's the fraction of energy density that's in the form of radiation. And that is almost, it's not much, 10 to the minus 5, 10 to the minus 4. In photons, it's 5 times 10 to the minus 5. And in neutrinos, it's 3 times 10 to the minus 5. The sum gives you 8.4. So photons are not contributing very much at the moment to the evolution of the universe. Matter has a value of about 0.315. And of that, baryons only contribute about 5%. Baryons are the stuff we're made out of. It's the stuff stars are made out of, galaxies are made out of. It's us. And so most of what we know about the universe is only determined by about 5% of the contents of the universe. Okay? So that right away should bring some red lights to your head. The dark matter, omega dark matter, is also part of the matter, and it makes up almost 27%. So the stuff that we call dark matter, and we don't know what it is 27% of the contents of the universe. Omega lambda, the dark energy, is almost 70% of the universe. And since if you sum these up, you get about 1. So that means omega naught is 1, and consequently the geometry of the universe is what we call a flat universe or Euclidean geometry. Now, be aware that we're assuming that we've included all the content, that we know what all the contents of the universe is, and that ain't necessarily so, possibly. It's an uncertainty. I'm just going to show you this. It's kind of complicated. I'm going to zip over it. So I'm going to give you a thumbnail picture of the evolution of the universe now, starting at the Big Bang right here, which I didn't say anything about because we don't know anything about it. But we had this inflation period where the universe just explosively expanded by maybe 25 orders of magnitude in a tiny, tiny fraction of a second. And then we had the formation of protons, and then we had nuclear fusion at these various ages. This time is running along on the bottom here, and you think of the size of the universe, if you wish, is the height. Okay, well, in any case, this is a kind of a thumbnail picture of what we've been talking about. And let's just now ask about the future. And there were 4 possibilities. If you think about the present is right here. When I was a grad student, we used to argue about whether the universe, although we knew that it's expanding now, its own gravity may have been enough, the density of matter was possibly large enough that it could actually collapse on itself and go back into a singularity. Other possibility is what's called a critical universe, where it's expanding outward as it goes, but it's never there's never a large enough density of matter to actually cause it either to come completely to a stop or certainly not to fall on itself. And then a coasting universe where it just continues out uniformly expanding. And the one that now seems to be the best assumption is the accelerating universe here, because dark energy has taken over and the universe is actually accelerating at the present time. So that's the one that the standard model now predicts. But there are many questions. How much might we be missing by only observing 5% of the contents of the universe? Might there be other undiscovered constituents? That is omega not equal to 1, as the current standard model would predict? What is dark matter? We don't really know what that is. What is dark energy? We also, why does dark energy behave like anti-gravity? Why is dark energy independent of the universal scale factor? As everything else, all other constituents in the universe depends on the scale factor, but omega lambda does not. And that has to go back to the mathematics of when it was, when Einstein introduced this lambda term, and he introduced it because the Friedman equation was unstable. So anyway, he thought it was his greatest error, but almost certainly was not. If neutrinos have mass, as experiments seem to imply, why have antineutrinos not disappeared from the universe? Another good question. What triggered the inflation of the universe, and what stopped it? We know basically essentially nothing about the Planck period and the laws of nature that govern the interaction of particles at this very earliest stage, and we probably are not going to know much more about it until we understand the quantum nature of gravity. Gravity is the one force that we still, believe it or not, it sounds simple, but it ain't, believe me. It's a very complicated issue, and we don't know how it would behave in a quantum sense. And so that's still a big open question. Fundamentally, why is the universe expanding? Okay, well, I stop there. I think I've taken your plenty of time, so thank you very much. I will be glad to take questions if you want.